Greetings and welcome, friends. Yesterday we were talking about this idea of solving equations, linear equations, using a graphical method or approach, which was kind of an interesting idea. And this is the way that it worked. We essentially, instead of solving algebraically, we broke these into two separate equations with a y attached to them. So I thought of them as two-dimensional rather than one-dimensional, right? So one of my equations would have been as such. The other would have been this one. Y equals x is actually graphically represented by this line here. Y equals negative 2x plus 3 is this line here because it has a y-intercept of 3 and it's going down 2 over 1. Let's see. No, that was almost a good line. You guys saw that. Nope, that's even worse. That's fine. Good enough for me. So what we would do, since I now represented both left and right-hand side as their own line, I then found the intersection between them, which this intersection is at 1, 1. All right, like solving a system of equations graphically. Now, I actually don't care what y is equal to because y didn't even exist in the original problem. All I really care about is what was x equal to. And the x for these is the x coordinate here. I get x equals 1 being the solution of this system and also the solution of the original equation. Let's do a check just to see if that works out. Is negative 2 times 1 plus 3 equal to, plug in 1 for that x as well, 1. So let's see, that'd be negative 2 plus 3 equals 1. 1 equals 1 is a true story. So it does check out. So this graphical approach for solving, yes, I agree it takes more work than our current skill set allows us because we could just solve this equation algebraically rather easily. But it's starting to branch into this idea that when you don't know how to solve something algebraically, you actually can represent it as multiple equations and solve it graphically, which is kind of a cool little feature. And let's take a look at problem nueve. All right, so same type of idea. Let's cruise through this because you guys are experts at graphing lines. So here we go. I've got y equals x plus 5. Over here, I'll write an equation. Y equals negative 2x minus 4. Ethan, you're writing this down, right? I'm doing this one? Yeah, doing it for you, friends. So let's see. What is the slope of the blue line? Just the one, just the one. And what is the y-intercept of the blue line? 5. So I'm going to start at 5 on my graph. If for some reason you didn't do the homework, you still should write this down. This is a great opportunity to learn, right? You're still invited to your education. Question, comment? I don't know. That's irrelevant. So let's draw this line. Ooh, right? Watch me move by my slope, right? We just start at the y-intercept. How about the purple line? Someone tell me the slope. Just the negative 2. Just the negative 2. It's all right. You could think of it as down 2 over 1 if you want to think of rise over run. And the y-intercept, friends, is what? Yeah, negative 4. So starting at negative 4. Hey, friends, we're all a team here. We're a team. So let's see. From the y-intercept, move by my slope, down 2 over 1, down 2 over 1. Yeah, it's negative, so you got to down 2 over 1. You also could go up 2 backwards 1, and that will find some points as well. So let's draw this line. We always run to the right, because that's typically where Mario runs. Sometimes. Yep, some levels. But the reason that rise and run are rise is up down for the y, right? And run is to the right typically is that this is the positive x-axis. This is the negative x-axis. So we're going to run to the right anytime my denominator is positive. And for the y's, here's the positive y-axis. Up would be rising, whereas down would be falling because that's the negative axis. If you need some more practice with plotting points, my man Khan Academy, he can help you out. Just search plotting points. Oh no, him and I, we are friends, I like to think. Because I know him. Salman Khan. I've seen a TED Talk by him. No, it's usually always him. So let's see. What is the intersection here? Yeah, -3, 2. Gentlemen, be quiet. Follow along. -3, 2 is correct. And I don't really care about the y. We just care about this x value here. So my solution is x equals -3. All right, a whole lot of work to solve this equation, but this strategy expands to even equations that we wouldn't have the skill set to solve, which is quite nice, I must say. So x equals -3 is the solution. I won't do a check for sake of time, but you could plug that -3 in for both of these x's, and it would come out true. We don't care for y because the original problem had no y in it, right? We were the ones that introduced the y's for the sake of solving it graphically. So for this, that's why we don't actually care about the y. We knew that they were going to be equal. Question? -3 was the x coordinate of their intersection, right? Over 3 up to. So we just cared about the x. All right, slightly trickier. Here's question 21. We can actually break this into two cases. All right, if you remember the absolute value equations, we can break this into one case where I'd have x minus 4 equals 3x, right, where this is equal to the same as that, and the absolute values were redundant or didn't do anything, or x minus 4 is equal to the opposite of that, right, because absolute value takes negatives and makes them positive. Or x minus 4 is equal, I'll be careful and write it this way. The only reason I am is that if you looked at example, what was it, 23, you would need to make sure you distribute this minus sign when you do the opposite. So I'm just going to show that there just for sake of camaraderie with example 23, as well as sometimes the problems are more difficult, so I want to make sure you're set to go. So if I'm writing equations for these, this one's going to be 1, and notice it actually shows up in each of these. So I'll have y equals x minus 4. I would have this be another equation, y equals 3x. I guess I'll write it over here. And what color did I choose last time? I'll choose green. This one, y equals negative 3x, is another one. Right, Cameron, you're writing this down? Yep. Last page. Last page. So y equals x minus 4, that's going to be a line that has a y-intercept at 4 and a slope of 1. So in this graph, it's this line. I'm over-explaining this problem, and in this graph, it's this line, because we could have actually just read the solutions right off the graph, but I figure, hey, we might as well continue to review these concepts, make connections while they're available to us. And then y equals 3x, the purple line is this one here. That's got a y-intercept. What is the y-intercept of that? Or if I was trying to read it off of this. Y-intercept is 0. That's why it starts at the origin. And it's going up 3 over 1 or down 3 backwards 1, if you want to think about it that way. Yeah. And then let's, my green line, you're probably guessing is this. Does that make sense? Is this the green line? Did they graph it correctly? Because their y-intercept is 0, which notice this has 0 as its b value, and the slope is negative 3, down 3 over 1. So my solutions, plural, are right here and right here. What are the coordinates of this point here? Oh, x then y. -2, then -6. And what are the coordinates of this point here? Yep, and x first. So 1, -3. So my actual solutions to this problem are x equals the -2 and x equals the 1. And I only care about the x coordinates of those points. Let me open up a Desmos and show you that if I didn't break this up absolute value style into these two cases, it is actually possible to graph the absolute values. And I just want to show that those work out as well. I'm currently typing in my other screen here. I'll pull it up here in a moment. 3, 2... Oh, there we are. Oh, that's my other homework video. So, if I graphed both of the original equations, right? X minus 4 inside an absolute value, right? That's the red graph. You guys might remember that was a horizontal shift to the right 4. That with that number, it was always the opposite direction than we'd think. An absolute value of 3x, it actually ended up with a horizontal shrink by a factor of 1/3. You also could have thought about this as a vertical stretch by a factor of 3. So if I wanted to find the solutions here, check this out. Oh, no, they didn't. Look at that. Thing of beauty. Thing of beauty. What do you notice? What do you notice? What's special about these points, friends? It's crossing 2 points, and what's special about those points? Yeah, they're actually, in this case, their y coordinates are different, but once again, we didn't care about their y coordinates, but their x coordinates give us the same solution. So whether I broke this into 2 cases and graphed all 3, and I graphed only lines, or if I remembered how to graph absolute value effectively, I could have graphed this side and this side separately and found the intersections and found 2 solutions at the same moment. So that's the power of solving by graphing. All right, thanks for watching, friends. Adios.